So good morning, everybody. Yeah, it's really my pleasure to speak at this workshop. It's a bit of a challenge because it's a very diverse workshop, and I think there's a wide range of expertise in the audience. So I think my job is to introduce a little bit of the excitement that's happening in AI for material science. So some of the concepts, and at the end I'll try to say where I think we are in terms of multimodal descriptions of materials. And I think what you'll see is there's probably a lot of commonalities with some other domains of interest. But maybe just to give my background, so I entered this field, I had an interest in chemistry and I had an interest in computers, and I realized you could actually use computers to solve chemical problems. And for a long time we were very limited by computing power, what the type of equations we could solve, and now AI is really changing how we approach sort of chemical research using computers. But I would say chemistry, similar to many different domains in engineering, we have master equations that describe many things. So we've mastered sort of partial differential equations, in this case from quantum mechanics, that describe the electron distributions, chemical bonding in every possible chemical system. Paul Dirac famously said almost 100 years ago that chemistry was a solved problem because all of chemistry is described by this equation. But of course, there's a caveat, and that's that the equations are too difficult to actually solve. So this was true 100 years ago, sort of with pen and paper, but it's still true now using the fastest supercomputers in the world. The many-body problem gets very complex, and you literally cannot solve the resulting equations. So in the field for many years, it was all about making approximations. So how can we go from sort of many-body partial differential equations to simpler equations that we can solve? And that's sort of been my evolution over time. So I'm interested in materials, I'm interested largely in crystals. And this is an illustration of a crystal of silicon. So you see the atoms of silicon and the electron density around those atoms. So if you want to describe this picture, you need to deal with wave functions, because electrons will obey quantum mechanics, and that's where the difficulty comes in terms of the solving numerical equations. One of the jumps we often make in the field is move to classical mechanics. Say, okay, the system is quantum, but we can approximate it by balls and springs. And so the atoms are connected, and we can solve that much more straightforwardly. And we can also evolve large systems over long times, solving Newton's equations, where you have spring constants that are informed by quantum mechanics. And that's one of the big branches in computational chemistry. What's really changing in machine learning is thinking about things in a different way. So how I think about it is we're replacing atoms by vectors. So those vectors are encoding the chemical information of those atoms, so the type of bonds that form, the type of environments. And then in machine learning, we have sort of a series of operations where there's information exchange between those atoms. So you vector operations between those atomic centers, and then you can essentially bypass the quantum mechanical equations. We can take data from quantum mechanics, we can train machine learning models that are incredibly fast. And that's sort of, I would say, the first wave of excitement in this field. It removed the bottleneck so we could scale our simulations. So instead of describing sort of tens of atoms in a box, we can now simulate tens of thousands or millions of atoms evolving in time. So on the left, you have an illustration of sodium diffusing in a component of a sodium-ion battery. And on the right, you have the behavior of a material used in solar cells, where the colors are representing sort of the instantaneous structure. And you can see it's not random. You get sort of these regions of red and blue, which we call nanodomains that occur in those materials. So I think one of the things that AI is doing is enabling us to run such large-scale simulations. But I would say the more important point is enabling inverse design. So this has been sort of a dream in material science for a long time, where we have an input to a simulation or to a code that's a set of properties we want. So this could be a material we want to substitute in a device, but we want to keep the same function. Or it could be a set of properties that haven't been observed yet, but we want to know, is there a material that could actually realize that combination? So it could be color, it could be corrosion resistance, it could be a particular conductivity level. So we want to map between the targets and candidates. So how do you do that? So I have a blue box, which is sort of the magic. I think we need 4 things. So we need data. So we need data that's going to connect between materials and properties. We need automation. And so this could be automation in terms of experiments that are going to make and test materials, but also automation in terms of simulations. So we can simulate very large data sets. We need models, so the connections between the variables in this case. So how does composition connect with structure and connect with processing, connect with properties? And then we need some type of selection algorithm. So in simple cases, it could be Bayesian optimization, if you have a small number of variables that you want to optimize against. But these days, often it's some flavor of genetic algorithms or reinforcement learning, that you have some reward that you want to optimize against and move closer and closer. So it's not really a one-shot prediction, but it's sort of an exploration campaign in order to give you the targets at the end. And just to keep things interesting, it's not an unconstrained optimization problem. So in chemistry, there is the periodic table, which represents sort of all of the available elements, but they're not equally available in terms of geographically and in terms of cost and availability. So you have this very skewed landscape. So if you want to develop a technology that's going to scale, then you have to look at the abundance and production of the elements involved. So that's going to limit the building blocks that you would use to design a material. But that would sort of essentially be a pre-processing step that you can introduce. And then the other side, I like to be quite efficient where I can. So it's trying to be effective in our use of computation. And I think there's an interesting trend for a while. It's sort of looking at the biggest supercomputers in the world, and that's what Top 500 actually tracks. But I really like this list, which is the Green 500. So you're looking at the fastest energy-efficient supercomputers in the world, at least open ones. And interestingly, Europe has actually been leading in this regard. So developing computer systems that are very efficient, that we can actually use for our simulations. So a lot of my group's work were actually performed in Isambard AI, so based in the UK. So I have 3 sort of short sections. So one, just to introduce a little bit more on machine learning for materials, how we can tackle this inverse design problem. And then I'll frame what I see as the multimodal challenge for materials. Okay, so I think many people in this room are more expert in machine learning than me. But what I would say, to frame it in a different way, so I spent a lot of my career working with quantum mechanics. So we're trying to solve these quite horrible equations. The inputs are simple, the equations are difficult. Machine learning is a little bit different because in this case, the functions are more simple, but from my perspective, more weight is given to the input. So that we really want feature vectors that encode chemistry quite well. And the more effectively the chemistry is encoded, the simpler the functions can be. So your model doesn't have to be sort of super deep. You can have something much more shallow if the input is actually effective. So that's where I've spent a lot of time thinking. And so just to give you an idea of how you would define such an input for machine learning for chemistry. So chemistry, we think of the periodic table. One of the key descriptors of elements is their atomic number. So how many protons and electrons are present in the materials. And that we can look up quite easily, but it's very minimal. If you look at modern periodic tables, we have a lot more information about each element. So information on its electronic configuration, the standard state of the elements, systems that react, systems that don't react. A lot of information gets encoded and taught in chemistry. So what we try to do for these inputs for machine learning models is to encode this chemical information in vectors. And so the data can be quite diverse. So you might have text data, so from published papers in material science. You can have information on compositions that are made and are stable, on structures and properties. And then you can choose some type of machine learning model that's going to take that information and encode it into a series of vectors for each element. And then you suddenly get a sort of a vector basis for the periodic table. So if I want to build a new material, it's going to be a combination of those vectors that will give me the input, and I might be able to predict the property very quickly, or a synthesis route. And I'd say there was an evolution in this field. At the beginning, about 10 years ago, people were hand-building these vectors. So we call it like local representations. So one of the popular ones is called MagPi. And it's basically for each element in the periodic table, you have a 22-dimensional vector. But each component of the vector has a physical meaning. So atomic number, space group of the standard state of that element. You see a variety of different things. And what people found is that this was a very effective input for supervised machine learning. So if you just took like a one-hot vector or some other description, it did much worse than taking this sort of chemistry-rich vector as an input. But clearly a human built this, and it's sort of quite limited in terms of the information that it encodes. So I would say the second wave of interest was moving to learned or distributed representations. So in those cases, you want to learn a continuous vector from a data source. One of the big successes at the beginning was this paper from my friend Annabeth Jain, where they took 1 million published papers from the scientific literature, and they used a word-to-vec model from Google, and then they trained a vector for each element, and it's based on the occurrence of those elements in the text corpus. So maybe copper appears next to conductor, lithium appears next to battery. You have all of these correlations that appear in the text. And they trained a vector set, which we call mat2vec. So it's a 200-dimensional representation for each element. And they used it predictively. So they could actually make predictions of materials that would be suitable for certain applications before they had been tested due to the similarities in that vector space, which is quite interesting. So we did something a little bit similar, so 200 dimensions again, but based on crystal structure databases and the connectivity between atoms in those databases. So what we call skip species. And you can see from these sort of, what you're here, you're looking at the cosine similarity between atomic vectors for each of those models. And you can see they encode quite similar information, or at least similar similarities, right? So the lead diagonal is just the element load itself, and the bright spots are elements that are similar to each other. And so one model trained on text, one model trained on crystal structure, and they end up giving quite similar relationships. And it turns out there's actually a whole family of these models. So what you can see, these cosine similarities for different published machine learning models for chemistry or for materials. Some of them are supervised models, some of them are unsupervised. There's a few generative models as well. They're all very different, trained on different data sets, but you can clearly see there's some similarities. Of course, some are much brighter, but they tend to recover the same type of correlations. So I was interested in this. We developed an open package, so building on the opening remarks, called element embeddings, to make it easy for people to play. So you can very quickly, just in like 2 lines, create an embedding for a given composition with your choice of model from the literature. And then the last point I'll say, so things have been evolving quite quickly. There's many different models that are published for materials and based on different architectures. So the vectors themselves are difficult to directly compare. So in this case, we have 3 different foundation models that have been reported. And this is just like a PCA looking at the distributions, and the colors represent our typical chemical classifications. And you can see they look quite different, right? They're different models, and they do sort of, the vectors are not directly comparable. But one of the things, so Zhenju Li, who's a Smith Research Fellow at Imperial, she had the idea to take some tricks from large language models and use these anchors, where basically we choose a set of materials and use those to anchor or give reference points to the space. And that defines a coordinate transformation. So you're trying to go from disparate models into a common reference frame. And she did it, and it actually worked quite well. So again, quite different models, that when you add these anchors, the chemical space starts to look very similar. So like one might be a graph neural network, and one will be a transformer model. And the vectors are really encoding very similar chemical information, which I think is quite interesting. Okay, so there was just a little bit of background to let you know sort of where we're coming from in terms of machine learning for materials. But yeah, one of my goals is being able to explore a very large space of both known and hypothetical materials. And the difficulty is diversity. So chemistry gets complex very quickly. So you can go from single element systems to multi-component. You can go from close packed structures to something very complex. So you have to be able to navigate this type of complexity. So to cut a long story short, generative AI has made a lot of progress in this field. One of the first tricks came with representation. So how do you really represent these 3D materials in a form that's suitable for generative AI? And the trick that came from Shay Tian, who was at Microsoft recently, and now he's at Project Prometheus, so the startup funded by Jeff Bezos, he put forward this scheme where basically we represent crystals as a combination of three factors. You have the atom types, which is something that's integer. You have fractional coordinates of those atoms, so where are they in 3D space? And then in crystallography, you also have the box or the lattice that describes the repeating unit of a material. So you have these three things are combined. And the idea is that you want to train a model that's able to generate a combination of AXL that will describe a material. And you turn this into a generative problem is that you learn the probability distribution of all Z, and then you can conditionally sample that probability distribution. And so that's where it gets interesting for materials design. So if you train a model based on all materials, you can then say, okay, I want a material that's glue. And then you should sample a Z for, it should return a material that would have that particular color, assuming the model was trained well. So that's sort of general concept. Where things have gone over the last year, and things move very quickly, is jumping into latent space. So the first generative AI models for materials are all based in real space. So you have atoms in space, they diffuse, and you form a material. Now it's all about encoding in latent space to make them faster and also make them more scalable. So yeah, I guess you get the idea. So typically what you do is encode, use something like a variation autoencoder to go from real space into a compressed space, and then all of the generative work happens in that compressed space. Okay, so my group's first model actually for generative AI for crystals happened to be multimodal. So a really talented postdoc, Hyun-Soo Park, who was very inspired by text-to-image models. So he joined my group and said, why can we not make a text-to-crystal model? So he decided to tackle this. So he built a data set of crystals and their corresponding text descriptions. And then he performed contrastive learning to learn to define the embedding space. So essentially he uses a text encoder, in this case it was Cybert, to encode text descriptions, and a graph neural network to encode the 3D structure. You perform contrastive learning. And then the vectors from the contrastive learning are used then to condition the generation process. So the denoising diffusion model, where you go from a random material on the left, which is just random atoms in a random box, and they diffuse to a realistic crystal. And it turns out this is actually very effective. So you'll see in 100 steps here, you go from the random sample to something that's chemically quite reasonable and actually very low energy. And this is something that would have taken supercomputer power before, but once this model is trained, it actually runs on a laptop. And you can start to explore very large chemical spaces very quickly. And it's sort of turning PhD campaigns into an afternoon on your laptop, which is totally incredible for people that have actually worked in this field. But yeah, what you're seeing on the screen there is the real space diffusion. Hyun-Soo wasn't happy, so before he finished with me, he developed the second version of his code. And this is where we go into latent space. So basically, there's a VAE that creates this compressed space. And then we perform diffusion within that latent space. But the trick he added on, which is quite genius, is when you go into the compressed space, the dimensions are lower. You can start to do reinforcement learning very efficiently. So this is a very effective way to strengthen essentially the conditioning. So the model would generate crystals. We'll calculate the properties or measure the properties. That will feed back into the generator. And then just even in 5 cycles, the strength becomes much stronger at producing realistic crystals with the target properties. Okay, and yeah, so this is more for the main users, but there's different ways you can use this. And it turns out, as you might expect, RL makes things much better when you look at benchmarks. So compared to the previous generations of codes pre-RL, reinforcement learning improves things a lot, but you have to be very careful with reward hacking. That RL is very good at finding tricks to increase performance. So we had to put in a lot of guardrails to make sure that diversity and novelty was obeyed in the results. Okay. So final point is going to sort of the multimodal challenge. But maybe as the starting point, I think beyond generative models, I think the most exciting thing right now in AI for science is co-scientists. So I guess if you've used Claude Code, sort of when it came out last year, at least when I used it, I got some special feeling that this was different. This wasn't just using an LLM. This was a model that would solve problems very effectively. And so what people are thinking is, can we start to use this type of agentic approach to solve scientific problems faster? And I would say there's 2 parts. So one is you have a reasoning engine. So this would be your reasoning model that takes in data, proposes a hypothesis, perform an experiment, and then it's going to loop. But the real trick here is that you'll need to have your scientific toolkit in order to do those experiments. So this could be a deep literature search. It could be data that you have access to that you've generated. It could be physical simulations. It could be machine learning models. Or it could be directly like an automated lab that's going to give feedback. And right now, there are many companies around the world that have been launched trying to develop this for different subdomains in materials. And actually, from my perspective, it felt like it reached a stage of what I could do alone in an academic lab. We could train models, but we couldn't really compete for this big picture. So that's why earlier this year, I joined CuspAI as the Chief Scientific Officer. So Cusp is a startup company, and they've been developing a materials intelligence engine to try to solve this problem. So example here, so you can put in a prompt, and that's going to trigger the use of a series of scientific tools to lead you towards a solution. And yeah, just to give you sort of a background, but just how fast this field has moved. So Cusp was established late 2024. It's out of date already. I think there's now 66 people. A lot of effort put into the data sets. So the internal data hold in Cusp now has over 40 million entries related to structures and compositions of materials. And actually now 7 offices. So the most recent one, San Francisco. I actually opened the London office in January this year in King's Cross. And we just filled it this week. So everything moves too fast. So now we have to think of more space. So things are exciting. Just to give you an idea of what we can do, we're trying to push atomistic simulations further. So working closely with NVIDIA to use GPUs very effectively. So we can do larger scale simulations over a longer time. And we actually released an open source tool called CUPS. Because yeah, startups like Cusp, they're benefiting a lot from open source software, the toolkits that have been built for deep learning and also for material science. So there is very strong motivation to give back to the community. So we decided that the community could develop this more than we could do alone within our company. But yeah, I would say the most recent work is building out our interfaces with experimental labs, and this we're calling CuspLink. And just to give you an idea of sort of the complexity that you face when you're actually dealing with experimental material science. This is an image of an automated lab in Imperial, one I'm part of called Digibat, that's led by Magda Titorici, and Jingyu is the technical lead. And you have a whole series of steps that you need to think about. You need to automate. You have different types of data coming back very quickly. And that's a challenge. And a lot of the initial work in labs like this is checking that a fully automated setup is as good as a human expert. So in this case, it's a lab that produces batteries, and are the batteries that the lab can make as good as the best scientist, in this case in Magda's group. And after some learning, actually the automated lab does really, really well. Actually the variability gets reduced a lot for the automated system compared to a human scientist actually making batteries themselves. Okay, so last 2 slides, I'll try to pull this together. So I think the challenge when it comes to data in material science, so one is that we have a multi-fidelity problem. So even if you're just interested in one physical property, and I'm putting bandgap here because I think Haiping has been interested in bandgap datasets. Bandgap is a property of a material, but it can be simulated and measured in different ways. And at least how I view it, there's sort of 3 different ways that we can create data: through experiment, through numerical simulations, or through machine learning models. But each of those sources has high fidelity and low fidelity variance. So you can have a very fast machine learning model that will make sort of a low fidelity prediction, or you might have one that's been fine-tuned and is going to produce something very accurate. So this is a challenge. If you get a very inhomogeneous data set that has a mixture of these, how do you deal with the different error distributions that are present in each of those data sets? I haven't fully got my head around exactly how we do it, but I know there are ways to solve this. And then the other side of it is it's a multimodal problem. So in material science and engineering, there are so many different techniques that are used to define and characterize materials. So there's many different perspectives. So one modality we have is text, because we have a lot of published literature. That can be quite valuable, and these days it's quite easy to process in terms of language models. And then you have data sets going from 1D to greater than 3D. So like X-ray diffraction is used a lot for characterizing the structure of materials, but that gives you sort of a low-dimensional representation, where if you go to tomography, you're dealing with sort of 3D voxels that are being measured. And then there's many combinations of these, like 4D STEM, that will go to even higher dimensions again. So I don't think we actually have a solution in terms of a multimodal treatment of data in material science. I think we know what the problem is. I think we need to generate better data sets, but we also need some smarter ways to then encode all of this information together and use it effectively. So then, yeah, my last point, I'd say in the UK, materials AI is really going through a special period. I think a lot of support from UKRI and the Henry Royce Institute on the academic side. We also have some good networks. So the Alchemy network, for those that are interested in AI for chemistry and materials, is very active. A lot of emerging industry. So Cusp is one of the companies. My friend Sam Cooper founded Polaron, which is another one based in London. It's also PhysicsX. And we have compute, but we always need more compute. So keep the pressure on funders to keep us resourced. But thank you for your attention.
Thank you for a lovely talk. Are there any questions in the room? Oh, right at the back.
So once you've designed the material, how do you know that you can make it? And how would you make it?
That was my question too.
Yeah,
Because I've done that.
So definitely these predictions should be validated, and I think the general trend, there's different solutions, but is that when you're predicting a material, it should be coupled with a prediction of how to make it, like the exact processing route. Because obviously the properties of material that's produced, it depends on the temperatures, it depends on the precursors that were used, exact process conditions. So I think there's an evolution of models from just predicting, oh, this is a perfect material, that's a solution, and actually giving a full recipe for how to make it. And that's something much more testable. And especially when you have these type of closed loop feedback, it's much easier to adjust them when you have this full, complete description. So yeah, should be coupled with testing, definitely.
Thank you, Aaron. I want to ask a question. It's about, we all know how AlphaFold has been built on PDB and CUSP competition and win the Nobel Prize. Do you see analogous problem in and AlphaFold-like moment in the material science field? And if yes, then what is the promising direction or problems? If not, why and what are the barriers? Do you predict whether there will be a Nobel Prize in the material discovery space, and how long it will take to make that actually a reality?
That's a seriously good question. If I knew the answer, I would be working towards that Nobel Prize. I would say one of the challenges here compared to AlphaFold is the distribution of data. So we do not have one central data resource that describes everything for material science. So what I show here, there are different data sets and sources for each of those experimental types, but there's not one sort of consolidated set. So there's not one grand challenge to solve. It seems in materials there are many sub-challenges that people are working on.
Are they all interconnected, right?
And they should be interconnected, but at the moment it's very difficult. So there's like some companies or labs that specialize in one technique, but to collect everything together, there are many barriers. But that doesn't mean, I think there can be some really big progress. And I think the Henry Royce Institute, part of their mission is to move towards a national materials database. So working closely with our national facilities like Diamond, Lightsource and ISIS, academic labs, and also trying to convince the big industries that it's safe to share at least some of their data, to try to bring things together for a national mission. And I think that needs to happen to have very clear data sets, very clear goals, to have that big success. But I think there's many challenges in materials that could lead to a Nobel Prize. And I'm pretty confident should I say that? Yeah, I am confident. And the next decade, I think we're going to see some big successes from AI that will deliver something Nobel Prize worthy in this domain.
Hopefully in the UK, right? So,
hopefully in the UK.
Thank you.
Was there a question? No.
Thank you. Really good talk. As a lapsed chemist, I enjoyed it very much. A fun question. So, if you could increase by a factor of 10 either your ability to do physical modelling or do the experimental verification, which one would you choose?
So I would choose experiment because there's always scaling issues with the simulations. And because of the hierarchy of approximations, doing more simulations doesn't mean you have better data or models. You get lost in your simulation world. I think we're really limited by experimental data right now. There's a lot of legacy labs that are slow and difficult to work with. There are some automated labs, but they tend to be very specialist. So I think getting high quality data and having validation. I think the big success is going to be like doing RL directly on experimental measurements. I think that's where we're going to see a breakthrough in this field.
Okay, maybe last question, and then I'll catch you up. I'll catch you before you leave. I've got lots, but mine are very specialised.
Hi. Okay. So my name is Sakib Ahmed. So I am not directly into the material science research, but I'm pretty much interested in the technical side. So I have seen like you have used like variational encoder and generated something from the probability distributions. Okay. So how do you like tackling or handling the hallucinations? Like from the probability distribution, it might be hallucinate for the material design or something. So how do you handle this sort of problem?
Yeah, that's actually one of the good points in this field. So when you use generative AI to generate or sample materials, we do have fast ways to evaluate. So we can calculate the energies of those materials. And I would say these days, maybe 5% of what's generated tends to be rubbish. That it generates atoms too close together or a coordination of ions that don't make sense. But 95% are quite valid. And then it gets more difficult to assess which are the best predictions. Because with generative AI, you're sampling the distribution. But I think it's now figuring out how we condition more effectively or use RL to then focus on the regions we really care about. But I think hallucination hasn't been a huge problem. They sort of talk about valid materials and invalid materials, but the invalid rate is very, very low now.
Oh, sure. Thank you.
Great. Thank you. Good question. Okay, so if are you around till
Mhm.
when are you going to disappear off?
Maybe at 2 o'clock. Or,
2 o'clock. So please grab Aaron at lunch, so I don't annoy him too much. And thank him again for an amazingly good talk.
Thank you.